So, hello everyone. I'm waiting for 5 minutes so that everyone can join. I will be starting in 5 minutes. So, okay, I will be starting the session now. Uh, Hello everyone. My name is Himanshi Singh. I'm from Department of Mathematics, IIT Jodhpur. Currently I am a research scholar here, and I'm doing my research in the broad area of probability and statistics. So today I will be giving you a brief recap about the topics which has been taught already in week 7 lectures, and then we will be discussing some of the problems based on those concepts. So so uh, let me start today's session. Basically, in these lectures, first of all, we've studied about the additive properties of the distribution. So basically, if I have x1, x2, xk random variables which are independent and following certain where each of the random variable is following certain probability distribution, then what will be the distribution of the sum of those random variables? So we will be discussing about those properties, and we will be considering some of the distribution which we have already considered or we have already discussed in the previous lectures. So here for the we will first of all we will be addressing the additive property of binomial distribution. So if I have x1, x2, xk random variables which are independent, and each of the xi is following the binomial distribution with size ni and probability p. So for each xi, the probability p is same; it is not varying. However, the size ni is changing. Then the sum of the random variable xi going from 1 to k will be binomial again, and it will be binomial with the size as summation of I going from 1 to k ni and with probability p. So it is the additive property of a binomial distribution. Now, apart from this, we have also discussed the Poisson distribution. So, if I have a random variables x1, x2, xk, which are independent and they are Poisson random variable, where each xi is Poisson random variable with parameter lambda I. So here the rate is lambda I and rate is varying for each xi. Then the summation of xi's I going from 1 to k will be again Poisson, and it will be a Poisson random variable with rate summation of lambda i's I varying from 1 to k. Apart from this, there is a relation between the geometric and negative binomial where so if x1, x2, xk counts the number of trials for the first success, then summation of xi will follow negative binomial with parameter k and p. So here it is an sk will be a negative binomial, means it will count the number of trials for the kth success. So this is the relation between the geometric and negative binomial. Now if I consider xi to be negative binomial, then if xi's are negative binomial, so in the next slide, so if xi's are negative binomial and they are independent of each others, and it is a negative binomial with parameter ri and p, means the probability of success is p, but xi will count the number of trials for the rith success. Okay, then the summation will follow again the negative binomial with summation I going from 1 to k ri and probability p. So here sk will count the number of trials for the summation I going from 1 to k ri, this amount, so this will be a number basically, so that success it will count and with probability p. So so this is the additive property of negative binomial distribution. Now there is again a relation between negative exponential and gamma distribution. So if x1, x2, xk are IID exponential lambda, so basically they are independent as well as they are identically distributed, means the distribution of all of the random variable will be same, that is exponential lambda. So then the summation of xi will be gamma k lambda. So basically exponential distribution was about so it counts the uh, time required for the first success. So basically x1, x2, xk counts the time required for the first successes. However, the gamma distribution counts the time required for the so not for the success, it was for the arrival. So it was so xi counts the time required for the first arrival. However, the summation of xi will count the time required for the kth arrival. So which is basically it was modeled by the gamma distribution, and here the rate will be lambda only. Now, apart from this, if I consider the gamma distribution again, so if all the xi's are independent and following the gamma distribution with parameter ri and lambda, then summation of xi I going from 1 to k will be a gamma with parameter summation I going from 1 to k ri and rate lambda. So this is basically the additive property of the gamma distribution. Now, apart from this, one of the important distribution was the normal distribution. So if xi's are independent random variables and each xi is normal, here for each xi we are varying the parameter, both the parameters, which is that is xi following the normal mu I with sigma I square for each I going from 1 to k. Then if I consider a linear combination of this, so it is so we are basically taking the linear transformation of xi, which is ai xi plus bi, summation is running from 1 to k. Then this will follow again, this will follow the normal distribution with mean as summation I going from 1 to k ai mu I plus bi, and variance summation I going from 1 to k ai square sigma I square. So this is a very important property of a normal distribution, because here we are considering the random variables to be independent only, and all the random variables are having different like all our random variables are normal but with different parameters. Like in the previous example, in the previous property in the gamma distribution, we are varying the ri's, but we are taking lambda or the rate to be constant. Now here we have this flexibility with normal distribution that we can vary both the parameters, the mean as well as the variance. So this is the linearity property of a normal distribution. And Then we already also studied this multinomial distribution. So in binomial so basically what this multinomial distribution was, like for binomial distribution we have x1 x2 dash dash dash, xn random variables here. So we are taking to be basically the n trials, and in n trials for each xi there is a possibility that there will be a failure or there will be a success. For x2 also there can be failure or success. So for each xi what we have, or for each trial what we have only two possibilities, that is failure or success. However, for multinomial distribution we are again considering the n mutually exhaustive, the n independent trials we can say. Then under identical condition we are considering, but the outcome of each trial can be k outcomes. Apart from this two, we can have k mutually exclusive and exhaustive events which this xi can result. So here we are taking this assumption and we are just modeling that what will be the probability of the joint probability mass function of this x1 x2 xn. So here we are considering that each trial may result in one of the k mutually exhaustive or exclusive events, a1 a2 ak, and pj denotes the probability of outcome aj. There we have that probability of success. We have all the p to be the probability of success and q to be the probability of the failure, which is basically 1 minus p. So here there only we have one parameter p, but now here we have pj, j going from 1 to k as the probability of the outcome aj. Now again we are taking xi to be a random variable which counts the number of outcome resulting in event aj. So xi will count the number of outcomes resulting in event aj. So j is equals to 1 to k. So then the joint PDF of x1 x2 xk minus 1 is given by this expression. So basically here why we have already only considered the k minus 1 random variables, because the last random variable which is xk random variable, which basically depends upon the value of the other random variables, because we have summation of xi to be equal to n, because total number of trials is n. So this total will be n. So xk will be nothing but it will be n minus summation of xi I going from 1 to k minus 1. So that xk we can replace it by this expression. So ultimately we only have this k minus 1 random variables. You can also notice this in the binomial distribution. There also we have already only there we have for xi we have two outcomes, and but we have only considered the probability x1 is equals to 1, and we have the PMF for that. So here also we are considering one random variable less because of this relation. Now this probability mass function is given by this expression. So it is n factorial p1 to the power x1, p2 to the power x2, pk minus 1 to the power x minus 1, k minus 1, 1 minus summation I going from 1 to k minus 1 pi. Here there was a term pk, but pk because summation of pk pi I going from 1 to k is 1. That's why pk will be 1 minus summation I going from 1 to k minus 1 pi. So that's why we have replaced that pk term by this term, and in power we have taken n minus summation I going from 1 to k minus 1 xi due to this relation, and divided by x1 factorial, x2 factorial, xk minus 1 factorial, again this term n minus summation of xi I going from 1 to k minus 1 factorial. So this is basically the PMF, the joint PMF of these random variable, and we just call this as a multinomial distribution. Now here if I consider the marginal distribution of these random variable x1 x2 xk minus 1, then that will be binomial distribution with size n, and it will be with size n and probability pi, where I going from 1 to k minus 1. Okay, because here also we have only considered the n times we have conducted the trials. So here also the size will be n, but the probability will be pi for I going from 1 to k minus 1. Then again, because of the binomial distribution, the expected value of xj will be n into pj, variance of xj will be n into pj into 1 minus pj. Now again, because we have here this xi is a random variable, then xj is also a random variable. Now we are considering this as a marginal distribution of this and marginal distribution of x2. Now if xi and xj we consider, then there will be covariance term also for that. So that covariance between xi and xj will be minus n pi pj, and the correlation between xi and xj will be minus of pi pj divided by qi qj whole to the power 1 by 2. Here also we are considering that I and j are not equal. So these are so this is the multinomial distribution, and these are the marginal distribution of the xi's uh, and the covariance and the correlation between xi's and xj. So this is basically a kind of generalization of the binomial distribution when the number of outcomes can be more than two. Apart from success or failure, other than those outcomes also, we can have many more outcomes. In that kind of scenarios, we use this multinomial distribution. Now, one of the special case of this multinomial distribution, where we say that these outcome to be these the outcomes for each of the trial can be 3. So here basically we have k is equals to 3, that we call it as a trinomial distribution. So this is when k is 3 in a multinomial distribution, then we call it as a trinomial distribution, and the PMF of it is given as probability x is equals to x, y is equals to y, and basically we have just replaced the quantities by x and y, and k the value of k to be 3, so we get this expression for the PMF. And here also we have this condition that P1 P2 is greater than 0, P1 plus P2 is less than equals to 1, and also so it will be equal to 1. Basically P1 plus P2 will be, no, it will be less than equals to 1, because we have 3, we have k is equals to 3, so it will be less than equals to 1. Yeah, then also x plus y should be less than equals to n. Now here again, if we consider the marginal distribution, so because of the previous results, we have x follows the binomial np1, y follows the binomial np2. Now apart from this, if I consider the marginals also, then sorry, not marginals, if I consider the conditional distribution, that x given y is equals to y, it will again be binomial distribution, and with size n minus y and probability p1 by 1 minus p2. If I consider y given x is equals to x, then this conditional distribution will be again binomial with the size n minus x and probability p2 by 1 minus p1. So this is basically a particular case of multinomial distribution, which is quite popular. Now apart from this, transformation of random variable was also introduced. So basically what we are taking a random variable, or we can say random vector. So basically if f is a function from Rn to Rm, that which is a measurable function, and also we are considering a random vector now, which is x1 x2 xn. This is a random vector. Then this function of this x1 x2 xn, which we are denoting it as a y bar, which is again a random, so it will again a random vector if this f is measurable. So we are considering f to be measurable, x to be a random vector, y to be a random vector, y to be a vector with transformation, which is a transformation of x1 x2 xn, and the transformation is nothing but this function f. Then this will again be a random vector, which will nothing but which will be again be a function from omega to Rm. Okay, now what we have a random variable x, we have just transformed it to a random vector y, y bar I can say. Then this random, what will be the distribution of this random vector, we do not know. Now, in order to find this distribution, how can we find the distribution of this random vector, which is basically a transformed random vector? So now, in order to find this, we have two approaches, or I can say two or more approaches. So first approach is MGF approach. So in the previous session, we have discussed that if I have y is equals to summation of xi, I going from 1 to n. So this is basically a transformation again. Okay, I have x1, x2, xn random vector, and I am just taking a function f, which is nothing, which is summing this one, and I'm constructing this y. Here, this is again a random vector, which but it only contains a one element only. Now this is summation of xi. Now if we had a theorem that if x1, x2, xn are independent, then this MGF of y was nothing but product of MGF of I going from 1 to n. We had this theorem. And now, so by this, if I know each of the random variable x1, x2, xn, the distribution of them, then I know the MGFs, and I can just product those MGFs and find out the MGF of y. Then this MGF of y will tell me the distribution of y, because it is a by uniqueness property of the MGF. So through that I can find out. So through that I can find the distribution of y. Okay. Apart from this, so this will not always work. So apart from this, if I want to find out the distribution of y, so there is a CDF approach also, that I can find out that probability. What is the probability x less than is equals to x? Then what is the probability? So this x, not x, if y is transformed, so y less than equals to y. Now y is nothing but this is f of x less than equals to y. Then again by sum of the transformation I can find out it in this form, x less than equals to something. Then I can find out that because I know the density of x, then I can find out. So this is a CDF approach, and there is also PMF approach. So now these are the approaches by which we can find out the distribution of y. However, one approach may not always be useful. Sometimes we use this approach, sometimes we use this approach. However, in order to tackle this, by the assumption of certain situations, we have this theorem, which we have already discussed for a function of random variable also. So this is again the generalized version. If we have in place of random variable, we have a random vector, then how this theorem will be. So if I have this random vector x1, x2, xn, so which is we are considering to be a continuous random vector with joint PDF to be fxx. Now I'm considering that let ui is equals to gi of x. Okay, so we are considering this to be a 1-1 transformation of, so we are considering transformation of this to be gi of x, which is equals to ui. So this is a 1-1 transformation. Now, because it is a 1-1 transformation, so there will exist an inverse transformation also. So from those inverse transformation, I can get x1 to be h1 u bar, x2 to be h2 u bar, and xn to be hn u bar, where u bar is nothing but u1, u2, un, which is an dimensional vector again. So it is defined over the range of the transformation. So basically what we are saying, that this transformation which we are considering this to be a 1-1 transformation, so that I can get the inverses. Now apart from this, we are assuming that the mapping, that is a mapping GI, and the inverse, that is this one. So that will be this the H1. So this is the basically the inverse. So these are both continuous. Okay. Apart from this, we are considering the partial derivative. So if I find out the derivative of this x1 with respect to u1 or u2, so those all the partial derivatives, they exist and they are continuous. Another assumption that this Jacobian, so the Jacobian J of the transformation, which is given as the partial derivative of x1 with respect to u1 up to un, and so similarly, we are finding out all the things. If n is 2, then it will be del x1 over del u1, del x1 over del u2, then del x2 over del u1, del x2 over del u2. So such type of this Jacobian will be formed. Now this Jacobian should not vanish. So it should not be equals to 0. Then we will say that the random vector, this u1, u2, un, is again a continuous whose joint PDF is given as fx of h1u, hn up to hnu, and the modulus value of this Jacobian. So basically, we will find out the determinant of this, and we will take the positive value. So which is the positive value of j. So this will be the PDF of the transformed random variable u bar. So this is the theorem which we will be using to find out the PDF of this transformation of a random vector. So this was a basic theorem. So you can also relate this when we have discussed the function of random variable. Here there we only have a single random variable, and such kind of theorem we have discussed for that scenario also. And this is a kind of generalized version of that, where the random variable is a random vector. Then in that case, we consider this. Now, apart from this, we all also discussed the we have also studied the concept of order statistics. So what is order statistics first of all? So if I consider x1 and x2, xn to be a continuous random variables which are identically and independently distributed, and whose CDF is of fx and PDF is small fx, then I'm considering y1 to be, that is x, and I'm taking it 1 to be in bracket to represent that this is the smallest element. So it is minimum of x1, x2, xn. Then this is y2. So y2 is the second smallest, y3 is the third smallest, and yn is nothing but the largest of all of them. So I'm considering this. So so we will get that x1 is less than equals to x2 less than equals to xn. Then we call x1, x2, xn to be ordered statistics. So basically we have ordered the random variables and we have taken this order, which is basically a we are taking the smallest first, then we are just increasing um, the increasing we are just taking the arrangement of the random variables such that it is in increasing order, so we say that it is in ordered statistics. Now the distribution of this xn, which is the maximum of x1, x2, xn, is given as the distribution of xn is equals to f of yn whole power n. So basically yn is nothing but we are taking this xn to be equals to yn. So we are taking this to be yn here. So f of yn to the power n. And the density is given as n f by n to the power n minus 1 f of yn, which is basically a like differentiation of this with respect to this yn. So this will be f of yn. Now the distribution of the minimum element. So if I consider this minimum as of x1, x2, xn, then the distribution is given as 1 minus f of y1 whole to the power n, and the density is given as n into 1 minus f of y1 whole to the power n minus 1 f of y1, which is basically again the differentiation. So these are the distribution of the maximum of x1, x2, xn and minimum of x1, x2, xn. Now, apart from this, we also have the joint density of x1, x2, xn. Now, since we have considered the all of them to be this independently distributed, so the joint density will be what? F of x1, x2, xn. So if they are independent, so it can be written as f of x1, f of x2. So sorry. So yeah, so if so the joint density will be f of x1, x2, xn. Now because they are independent, so it can be written as f of x1, f of x2, f of xn. So the joint density can be written as product of the I can say the marginals. Okay. Now if I consider the joint density of y1, y2, yn, then by a certain proof, it was proved that it is equals to n factorial and the product of f of yi going from 1 to n. Okay, so this is the density of y1, y2, yn. Here we have all the yi's are in order. So this is y1 less than y2 less than yn, and they are ranging from minus infinity to infinity. So these were the joint densities for both of them. Apart from this, what will be the marginal of yr? So if I consider the marginal density of yr, so it will be yr. So this is n factorial. So this is basically the rth. So if I have this to be the smallest, this is y2, and there is something, this is some yr which is between all these. So this is basically greater than yr minus 1 and less than yr plus 1. So the density will be n factorial divided by r minus 1 factorial, n minus r factorial, and this expression, which is already been discussed in the lectures. Apart from this, if I consider two of them, yr and ys, then the joint density of this is given by this expression. So if any yr, so if I know so if I want to find out the joint density of the second smallest and third smallest element, then I will just put the value of r to be 2 and s to be 3, and I can find out the joint density by using this. Now because here this is basically the function f of yr, and this is basically a cdf of, which is given, cdf of x size, so which is already given. So I have the knowledge of these things, I have the knowledge of this thing, only I do not know that what is r and s. If I put it here, then I can get the expression final, which is the joint density of yr and ys. So this was basically about the joint density between two of these random variables. Now, apart from these, sampling distribution topic was discussed. So basically, what is sample and what is the sampling distribution here? We'll discuss it. So what is first of all population? What do we mean by the population? So basically, it is a collection of measurements on certain characteristics. So if I have like a population, or I can say if I want to consider heights of the individuals, so I will consider, if I will go to every individual and say what is your height, so 5.2 5.2 feet, 5 feet 2 inches, or 5 feet 3 inches, and all these measurements I will take. Then I say that if I take all the measurements, so that will be the population for my experiment, that will be the population. So it is basically the collection of the measurements on certain characteristics. Now sample, so it is a subset of a population. Now from all of the heights, I just took a sample. Maybe I take 10 measurements. Okay, I take 10 measurements, then that I will say as a sample. Okay, so this is basically a subset of population. I can take 10, 12, 15. So it will be a sample until unless it is, so it will be a sample provided that it is basically a subset of the whole population. Now, apart from this, what is a random sample? Now sample can be taken any like any, I can take any 10 observations or any 12 observations, so that is a sample. But what is random sample, which basically we are concerned about? So if I have x1 x2 xn, n independent and identically distributed random variables, where the probability distribution for each of the random variable is same, that is fx, then I will say that x1 x2 xn is a random sample from a population with distribution fx. So basically, if there is a population whose distribution is fx, now I took n samples which are independent and they are identically distributed, means the distribution of each of the xi is fx. So then I will say that x1 x2 xn is a random sample from a population with distribution fx. So this is basically the probability distribution of that statistic will be sampling distribution. So some of the sampling distribution were discussed further. So that is, first of all, the central limit theorem. So basically, if I give this example, so if I give example of this, so if I consider x bar, that is summation of xi 1 upon n, I going from 1 to n. Okay, so this x bar, so this is basically a statistic. Now, if I know that xi follows some, if I say normal distribution, okay, 0, 1, then I can find out the distribution of the x bar. Then the distribution of x bar will be sampling distribution. Okay, so that will be the sampling distribution if I say about the example. Okay. Now, apart from this central limit theorem, which was very important theorem, which has been discussed, that if I have n independent and identically distributed random variable with mean mu and variance sigma square, then xn, I'm considering xn bar to be the mean, that is 1 upon n summation I going from 1 to n xi, then the limiting distribution of under root n xn bar minus mu upon sigma, the limiting distribution of this will be a standard normal as n tends to infinity. Basically, limiting distribution means that if the sample size increases, so if I can go on increasing the sample size and going towards the infinity, then the distribution of this quantity, that is xn bar minus mu upon sigma, and there is a root n also in the multiplication, so that the limiting distribution of this will be normal 0, 1. That is a standard normal, which is, we have already seen that it is little easy to tackle with, and we also have the tables. We just fit this normal distribution to anything and just find out the values of the probabilities. So how much large n should be considered? So in practice, n greater than equals to 30 is considered to be large. So if n is greater than equals to 30, we can consider it to be large, so that we can find out the limiting distribution of this quantity. Now, if the original distribution is close to normal, now if the original distribution is very much close to the normal, then for smaller n also, this approximation will give a better result. Okay, it will be easy to handle with, and it will give a result which is very much like close to the true one. So this is the importance of the central limit theorem, that we can consider the random sample for any population, and we just find out the as n is, if the n is large means the sample size is large, then we can have the limiting distribution of this quantity to be the standard normal distribution. So there is a corollary to this theorem, that if I have two random samples, x11, x12, x1n1, so this is a sample of size n1 with with mean mu1 and variance sigma1 square, and I have again a different sample x21, x22, x2n2 of size n2 with mean mu2 and variance sigma2, and I'm considering x1 bar to be the mean of this or average of these random samples, and or random variables, and x2 bar to be the mean of this, that is 1 upon n2 summation I going from 1 to n x2I. Then the limiting distribution, so this is n1. So this is n1 here, this is n2. Then the limiting distribution of this quantity, that is x1 bar minus x2 bar minus mu1 minus mu2 divided by under root of sigma1 square by n1 plus sigma2 square by n2. So this will be normal 0, 1 or standard normal distribution as n1 and n2 goes to infinity. So this will be the normal distribution. So I hope my voice is clear, because there is no response to from anyone. That's why I'm confused a little bit. My voice is clear, and the things you are getting. Just confirm it. Okay. So then chi-square distribution was also studied, so also given. So if I have a continuous random variable, so we say that it follows a chi-square distribution with n degrees of freedom if its PDF is given as 1 upon 2 to the power n by 2 gamma n by 2 e to the power w by 2 and w to the power n by 2 minus 1, where w is greater than 0 and greater than 0. Then this is basically the chi-square distribution. The density is given like that, and this is basically a special case of a gamma distribution with parameter n by 2 and 1 by 2. Here the expected value of w is n, variance of w is 2n, expected value of w to the power k is n into n plus 2, n plus 2 into k minus 1, and the moment generating function is 1 minus 2t to the power minus n by 2, t is less than 1 by 2. So these are basically the chi-square distribution, and why is it important? I will be discussing it further. So this is basically called as a sampling distribution. So this is the distribution of a certain like statistic, which is a very important statistic. So we will be discussing the chi-square distribution a little in the next slide. So before that will be this the additive property of the chi-square distribution is what? So if I consider w1, w2, wk to be independent chi-square random variables with so each wi is a chi-square with ni degrees of freedom, then the summation will again be a chi-square distribution with summation I going from 1 to n ni degrees of freedom. Now, chi-square distribution and normal distribution has a relation, which is a very important one. So, if x1, x2, xk are independent random variable where each xi is standard normal. So, here each xi is standard normal random variable. And if I consider the summation of xi square, so this summation will again be a chi-square distribution with k degrees of freedom. So, this is very important. So you can see that this is basically a sample, sorry, statistic. It is a function of samples. So this is basically a statistic which is following chi-square with k degrees of freedom. Okay. So they both are statistically independent, and due to this result we have so by using these results we also have this, that x1 x2 xn are independent random variable, then y is equals to x bar and s square, which is nothing but 1 upon n summation xi minus x bar whole square. So this y and s square, they both are independent. Okay.
Ma'am, sorry
Yes.
to interrupt.
Yeah.
Actually, your voice was like there was some error, and after like there was like big gap between that x. If an x follows normal distribution from 0 to 1, then x square will follow a chi-square distribution.
Yeah.
Right after that, there was a gap. So, what did you
Okay,
thought?
okay. So yeah, so I said that if x1, x2, xc are independent random variables where xi is following normal standard normal distribution, so then if I take the summation of I going from 1 to k xi square, then this summation will follow the chi-square distribution with k degrees of freedom. Okay. So
Sure.
if I only consider this x1, like if I have a x1 follows normal 0 comma 1, okay, then if I consider x1 square, then this will again be a chi-square distribution with 1 degree of freedom. Okay, now if I consider each x1 square, x2 square, x cube square, so each will be chi-square with 1 degrees of freedom. Now if I consider the summation of this one, the summation each one is chi-square 1 degrees of freedom. Now by this one we have the summation to be chi-square k, because the sum will be k. Okay, so this is basically the summation of I going from 1 to k xi square follows chi square with k degrees of freedom.
Sure.
So
Thank
if there is any like if there is any lag, the voice is not clear to you or something like that, then just let me know, because there may be a internet problem or something like that. So that is important to me also to record all these things. So just let me know about this. Okay.
Yes.
Okay. So apart from this, we have this theorem that if x1, x2, xn are independent random variables and each xi is normally distributed, normal mu comma sigma square. Now, if I consider y to be x bar and u is a random vector u1, u2, un, where each ui is xi minus x bar. So this y and this u bar, they are statistically independent. Okay, so they are statistically independent. Now, because of this result, we have a more important result, that is, so basically it is a corollary to this theorem, that if x1, x2, xn are independent random variables with xi following the normal mu sigma square, then if I consider y to be x bar, okay, s square to be 1 upon n summation xi minus x bar whole square, which is nothing but a function of this u bar. Okay, because each argument is xi minus x bar. So what I'm taking the summation of I going from 1 to n, and I'm just making the square of xi minus x bar, and I'm taking 1 upon n here. So now this s square, which is this, so this y and s square will be independent because of this theorem. Okay, now from this theorem, we have this important result, that n minus 1 s square. So here it is n minus 1, not n. So if I take n also, then this is true. If I take n minus 1 also, this is true, because this is basically a scale, we can say. So n minus 1 s square by sigma square, this follows chi-square distribution with n minus 1 degrees of freedom. So which is basically used when we estimate the sigma square, which we will be discussing in the further lectures. So when we estimate the sigma square, then so in when we find out the confidence interval and all those things, so this distribution will be a very important distribution. And this chi-square, we have this chi-square tables and all these things from which we can calculate the values of this. So basically the chi-square distribution is like this. So if I have this point here, I say that this is chi-square alpha. If I want to find, this is basically alpha. So basically this is probability that, so if this point is x alpha, probability that x alpha is greater than is equals to x. So if I want to find out this, so this will be alpha. So the probability here will be alpha, and the tables for this is given like as that of the standard normal distribution, which we have already discussed. So we will be discussing these things further in the next lecture in a more detailed way. So till now we have discussed all the concept which has been already discussed in the lectures. So if there is any doubt or something, you can ask. So okay, so if there is no doubt, then I will be starting with the questions. So, uh, so this first question is, so x1, x2, xn are independent and identically distributed random variable which follows exponential distribution with mean 1 by beta. So each xi follows exponential distribution with mean 1 by beta means rate is beta. Okay, exponential beta. Now we need to find the expected value of x1 square, which is the minimum. So x1 is the smallest of x1, x2, xn. So I need to find out. And if I need to find out this expectation, then for that I should know the distribution of x1. So if I need to find out that probability x1 less than is equals to x. So this is basically the smallest element is less than is equals to x, means that the every element x1 is less than is equals to x, x2 is less than equals to x. So I can say to be, since it is a continuous distribution, so it does not make any effect. X2 or x3 less than x to xn less than x. Okay, so this is because x1, x2, xn are independent, so I can say to be I going from 1 to n, probability xi less than x. Now, what is this? This is basically the cumulative distribution function of xi. So if so, we have this exponential distribution. Xi follow as exponential beta. So what will be the density? Density. What will be the density of exponential distribution? So it is lambda, or I can say here we have rate parameter to beta. So I have this beta e to the power minus lambda. Oh, beta will be beta here into x I. So the exponential density was lambda e to the power minus lambda x. Okay. So here because the rate is beta, so we are putting it beta, and here we have taken this in the argument to be xi, so it will be xi. So this is basically the density. But here we have the distribution. So this is basically product I going from 1 to n f of xi x. Okay, so this is basically the distribution. So what we will find out, let me use x here to avoid. So this is just the notation. We can change it. We should know that what we are. Take outside, and if I can write it as t also. Okay, so it will be t here. So if I take the upper limit, so it will be e to the power minus beta x, and lower limit here, so it will be minus of 1. It is nothing but 1 minus e to the power minus beta x. So this is basically the distribution, the CDF. So I will put it here. So it is probability x1 less than x. So that is equals to product of I going from 1 to n, and it is the expression that f of xi x. So we are just taking to be 1 minus e to the power minus beta xi. Okay, so this will be the CDF, and we need to find out the PDF now. So what we will do? Okay. So I'm thinking that I've made some mistake here, because this is the minimum of x1, x2, xn, and which is less than x. Okay, I made a mistake. So what I will write it here, that minimum is less than x, which is implies that 1 minus probability that x1, because if minimum is less than x, I cannot say that each element is less than, because it is minimum. So it can be less than x, but other elements can be greater than x. So that interpretation was wrong. So here I will take it in a different way. So I will just take 1 minus probability x1 greater than x. Okay. Now I can say, okay, I'm sorry. So now I can say, because here what we are saying, that minimum is greater than x. Now if the minimum is greater than x, then every element will be greater than x, because the minimum quantity is greater than x. So it will be 1 minus probability x1 greater than x, x2 greater than x, and xn greater than x. Now I can write that this is 1 minus, because x1, x2, xn are independent, so I can take I1 to n probability xi greater than x. Now I can replace this as 1 minus product of this thing, 1 minus probability xi less than is equals to x. Okay, so I just replace probability xi greater than x to be 1 minus probability xi less than is equals to x. Now this is the distribution function. So the format will be, oh, here I should replace it. So here it will be probability x1 less than x is equals to 1 minus product of I going from 1 to n, 1 minus f of xi x. So I've just replaced this quantity as a CDF. So fxx. Okay. Now this quantity I have this. So this will be 1 minus product I going from 1 to n. So 1 minus this quantity. So it will be e to the power minus beta xi. So this will be equals to 1 minus, since we are doing the product, so e to the power minus beta into summation of xi, I going from 1 to n. Okay, because these are in product and we are just these are in power and we are product finding out the product, so it will be the summation in the exponential the power of the e. So it will be this quantity. Now this is probability x1 less than x. And what I need to find in the question, we need to find the, since I need to find the expectation, so I should find the density. So in order to find the density, I will just, because this is a CDF of x1, so I will just differentiate it with respect to uh, with respect to x. So, or I can say that this probability x1 less than x is equals to 1 minus beta summation xi. Okay, now if you see here this was a distribution of exponential with parameter beta. Okay, now this was a distribution function with respect to with exponential distribution with respect to beta as a parameter. Now here again this follows exponential distribution with parameter as beta. Okay, wait, I made some mistake here. So it was not xi here. It was, so since we are considering the same x for all, so it will be x here only. So it was, so here it will be summation of x. So it will be n of x. So it will be, because here we are considering argument to be x only, and here it is 1 minus e to the power minus beta x. So there is no role of this xi, and they are because they are independent, so we can take this product, and I just take this product in the exponent term, and I just wrote it as n of x. Now it will be minus beta n of x, n into x. So it follows exponential distribution with n into beta parameter. Okay, now so this implies x1 follows exponential with n beta. So the density of x1 will be what? It will be n beta e to the power minus n beta of x. So this will be the density, or I can say, oh yeah, we can say it to be x. So it will be n beta e to the power minus n beta x. Now, what I need to find out? I need to find out the expectation of x1 square. So expectation of x1 square will be integration over x square into fx1 dx, and the integration is running from 0 to infinity. So it will be integration of x square e to the power minus n beta x n beta dx. So or what I can do, I can just find out this integration, or what I can do, since x1 is exponential with rate n beta, so the expectation of x1 will be what? Because it is exponential distribution with n beta, so the mean will be 1 by n beta. And the variance of x1, so this is another approach, that this is 1 upon n square beta square, because for the exponential distribution we have mean to be 1 by lambda and variance to be 1 by lambda square. So here the lambda is n beta, so the mean expected value will be 1 by n beta and the variance will be 1 by n square beta square. Again, what I can say, that expectation of x1 square minus expectation of x1 whole square, this is variance of x1. So from here also I can find out this expectation. So basically expectation of x1 square will be, so variance of x1, so not square, it is, yeah, then so it will be, this will be variance of x1 plus expected value of x1 whole square. Yeah, so it is 1 upon n square beta square plus 1 upon n beta whole square. So it will be 2 upon n square beta square. So the expected value of x1 square will be 2 upon n square beta square. Yeah. So the variance was different. So variance of the exponential distribution was 1 upon lambda square, and the mean was 1 upon lambda. So it is the expected value of this to be 1 by n beta, and variance is 1 by n square beta square. So is there any doubt in this question? My screen is visible to you?
Yes, ma'am.
Okay, so you understood this this question. There is any doubt in this question?
No doubts, ma'am.
Okay, so I'll move forward for the next one. So if x1, x2, xn are independent random variable with xi's following normal distribution with mu sigma square, then what will be the distribution of this quantity? So just you guys tell me what will be the distribution, or how can we find out the distribution? This is just based upon the results which I have already discussed in the in the beginning of this class. So what will be the distribution of this thing? So if I cut it short, what will be the distribution of xi minus mu by sigma? Just tell me once. Xi is following normal mu comma sigma square. Then what will be the distribution of xi minus mu by sigma? What will be the distribution of this?
Standard normal.
So it will be normal 0, 1. Okay. Now if I consider xi minus mu by sigma whole square, so it will be
Chi-square.
chi-square. Chi-square with how many degrees of freedom?
Yeah, okay. 1 degree of freedom.
1 degrees of freedom. So it will be chi-square with 1 degrees of freedom. Now if I find out the summation of xi minus mu upon sigma whole square, I varying from 1 to n. So basically I am adding chi-square distribution with 1 degrees of freedom plus chi-square distribution with 1 degrees of freedom. Then it will be what?
Chi-square distribution with n minus 1 degrees of freedom.
N minus 1 or N?
And sorry.
Yeah, so it
Yeah.
will be n degrees of freedom because we are adding n number of
Yeah.
standard normal, the square of standard normal distributions. So it will be chi-square with n degrees of freedom. So since it is a chi-square distribution, we know what will be the expected value of y.
2p raised to power.
As it, how many?
Sorry, it was variance.
So expected value of y is basically the mean, and mean of the chi-square distribution is equals to the number of degrees of freedom. So the degrees of freedom. So this is
Correct.
n. And variance for a chi-square random variable is twice of n. So this can be proved. This has also been discussed. This can be proved, but directly because chi-square distribution is very common and very like useful. So you know that expected value of a normal distribution is mu and variance is sigma square. By the same thing, you just learn it that the expected value of y for a chi-square distribution with n degrees of freedom will be the number of degrees of freedom, and the variance will be twice of the number of degrees of freedom. So it is easy. It is not a very that tough expression to write to learn. So you just like just remember these two things. Okay. So it is chi-square random variable with expected value as n and variance as 2n. So this is basic question which is just depend upon the concept which we have already like, discussed. So I will be moving for the next question now. So yeah, so carbon monoxide emissions for a certain kind of car vary with mean 3.5 and standard deviation 0.4. So we have mu to be equals to 3.5 and standard deviation that sigma is equals to 0.4. A company has 80 of these cars in its fleet. So 80 of these cars acquired randomly from various sources. So from various sources, these 80 cars are acquired. So basically, we have sample of 80 cars and n is equals to 80. Okay. So assume that CO emissions of cars are normally distributed. So the CO emission. So if I consider X I, or I can say if I consider X to be the CO emissions. Okay, then X follows normal distribution. Okay, with mean 3.5 and variance, I can say 0.4 whole square. Now find the probability that a randomly selected car. So basically, we are selecting only single car. Okay. So what? So if I have this x1, x2, dash x80. So I'm just taking one, only one, not all the. I'm not talking about all the 80s or the mean or anything. I'm just saying that find the probability that a randomly selected car, that is, I can say xi, or so xi is an any randomly selected car from the fleet has a CO emissions in excess of 3.9, in excess of 3.9. So I need to find the probability that xi is greater than 3.9. Okay, so so there is a because n 80 are given, so you just don't confuse that with whether we need to find out the summation or something like that. We are just taking only single value xi. So I need to find that probability xi is greater than 3.9. So I will just convert this into a standard normal random variable. So that is xi minus 3.5 divided by 0.4. So that will be a standard normal distribution. This is greater than 3.9 minus 3.5 divided by 0.4. So it will be probability z greater than, so it will be 0.4 divided by 0.4. So it will be 1. So which is 1 minus probability z less than 1. So which is nothing but 1 minus phi of 1. And we can also find out this probability directly from the standard normal table and just subtract it and just find out the answer. Okay, so this is basically about the standard novel, how to make the. We have also discussed these things in the previous lecture, but here the different thing was that the company has a 80 of cars, which depends upon the concept of the samples, which we have not discussed previously. So if a company has 80 cars, means we are taking a sample or I can say the population is 80 and I'm taking a single sample xi, which is greater than 3. I need to calculate the probability that that sample is greater than 3.9. And what I will do, I will just make that to be a standard normal and find out the probability. Okay, is that okay? Okay, then I'll move forward for the next question. So this says that if x and y are bivariate normal distribution with common mean mu. So x comma y, this follows bivariate normal distribution with common mean mu. So we have for x mu, we have for y mu. Common variance 1, variance is 1, and the correlation, or not correlation, so the rho xy is 1 by 2. Yeah, correlation I can say 1 by 2. So this is the bivariate normal distribution, x and y is following. Now since x and y, first of all, x and y is bivariate normal, then in that case, x follows the normal distribution with mean is mu and variance 1. Y also follows normal distribution with mean mu and variance 1. Okay. Now, what I need to find, that I have given that probability x plus 3y is less than or equals to 3 is equals to probability 3x minus y greater than or equals to 6. And I need to find mu. What will be the mu? Now for that, since this is the probability x plus 3y less than or equals to 3. Okay. And this is probability 3x minus y greater than or equals to 6. I need to find out. Now if I go it like that, like if I find out that what is expected value of x plus 3y and what will be the expected value of 3x minus y. So just tell me what of x and y are both are normal, then linear combination will again be a normal random variable. So x plus 3y will be a normal random variable, but what I will do, I will just make them to be standard normal random variable. Okay, now in order to make this random variable to be standard, I will just subtract its mean from itself and divide it by the standard deviation. So in order to find the mean, and so for that I need to find out the mean of x plus 3y, mean of 3x minus y, and their variances. So what will be the expected value of x plus 3y? I'm asking to you, you just know, you just let me know that what will be the expected value of x plus 3y. So how can we find out that?
By linearity property.
What?
By linearity property, ma'am.
Yeah, by linearity property. So it will be expected value of x plus 3 times expected value of y, because expectation is linear. So I will just take it inside. So it will be this. Now what is expected value of x? So here, what is expected value? So x is normal random variable with mu comma 1. So here, what is the expected value of x? For a normal random variable, the expected value of x is mean, nothing but the mu parameter.
Yes, ma'am.
So it will be mu, and y is again the same random variable with same distribution. So this is again mu, so it will be 3 mu, so it will be 4 mu. Now similarly, if I find out the expected value of 3x minus y, so it will be 3 times expected value of x minus expected value of y. So it will be what?
2 mu.
2 mu, yeah. Okay, now expected value is we found out. Now what will be the variance? Now if I need to find out the variance of x plus 3y, then by the property of the variance, what we have, that it will be variance of x plus
9.
9 times variance of y, because the square of 3 will come outside. You know this thing, na?
Yes, ma'am.
Yeah. Then it will be plus twice of covariance between x,
X3
comma 3y.
into
Okay.
rho.
Now there is a property of this the covariance, that this 3 can come outside. If there is any scalar in the multiplication of any of the random variable, it can come outside. Okay. So the variance of x plus 3y will be, variance of x we know it is 1. Okay, variance of y we know it is 1, so it is 9 plus twice, so it will be 3 will come outside, so it will be 6 times covariance of x comma y. Now covariance between x comma y will be what?
Rho into sigma x sigma y.
Yeah, so rho into sigma x into sigma y. So rho we have 1 by 2 and sigma x sigma y we have 1, so it will be 1 by 2. So variance of x plus 3y will be, so it will be 1 by 2 here, so it will become 3 here, and 9 plus 1 10, so it will be 13. Okay, so it is 13. Now similarly just find out that what will be the variance of 3x minus y. That will be 9 times variance of x plus variance of y. Due to this minus sign will come it here, minus twice of covariance between 3x comma y. Now this 3 will come outside, here it will become 6. Covariance between x and y, so that will be 1 by 2. So again this term will be 3. 9 times variance of x is here 9 and it is 1. So 9 plus 1, 10, minus of, here it will be
3,
3. So it will be
7.
7. Okay, so this is the variance and this is the expectation. Now what we will find out, we have that probability, okay, probability x plus 3y less than is equals to 3 is equals to probability 3x minus y greater than is equals to 6. Okay, now I'll subtract the mean from itself, if the expected value or the mean. So it is 4 mu for x plus 3y. So it will be minus 4 mu divided by the standard deviation, which will be under root of 13. So divided by under root of 13. And we will subtract and divide it here also. This is less than is equals to 3. So 3 minus 4 mu divided by under root of 13. Here the mean was 2 mu, so it is minus 2 mu divided by the variance was root 7, so it is root 7. So it is minus 2 mu by root 7. So basically what it is probability z less than is equals to 3 minus 4 mu by root 13 is equals to probability z greater than is equals to 6 minus 2 mu by root 7. Okay. Now, if I see the standard normal table, so this is a standard normal table, sorry, the standard normal curve, then this is 0 basically here. Now, it is saying that this is some point. Now, if I take the probability of the area which is less than is equals to this point, and if I take the probability area which is greater than is equals to this point, then both of the probabilities are equal. So when it happens, if I say the standard normal curve, then if some point is here and if some point is here, okay, then if I consider this to be let's say minus a and this to be a, then probability z greater than is equals to a means this area, and probability z less than is equals to minus a means this area. The probability uh, or I can say that the area, this area and this area will be equal when these points are like opposite in sign of each other. Okay, so if I take the probability z to be greater than is equals to this quantity and z to be less than is equals to this quantity, then both of them must have the relation that this is negative of this or this is negative of this. You understand this?
Yes, ma'am.
I'm sorry, guys. There is some issue in the network today. That's why it is like keep reconnecting. So till now, where I have just till where you have understood the question.
That the probability of A minus and probability of minus and probability of A is equally under a
Yeah.
standard normal
Yeah, so
distribution.
if you are seeing this standard normal curve, then if this kind of situation is arising, that probability z less than is equals to something and probability z greater than is equals to something are equal, then those points should be negative of each other. So you understood this thing. So
Yes, ma'am.
is this clear? Yeah. So then what I can say, that 3 minus 4 mu by root 13 is equals to 2 mu minus 6 by root 7. So I'm just taking negative of this quantity. You can take it in a different way also. You can take negative of this quantity also, because you do not know what A is and what minus A is. So I'm just taking the negative of this quantity. So this will be the negative of each other. Now if I solve it, what will be the expression for mu? You just find out. So it will be like 3 minus 4 mu into root 7. Just cross multiplying it. And 2 mu minus 6 into root 13. So it is 3 root 7 plus 6 root 13 is equals to 2 root 13 plus 4 root 7 into mu. So what will be the mu? So mu will be 3 root 7 plus 6 root 13 divided by 2 root 13 plus 4 root 7. So this is basically the mu. Is that fine?
Yes, ma'am.
Yeah. So okay, so we are done with this question also. So I will be moving forward towards the next question. So here what we have two random variables which are IID, means they're independent and they are identically distributed with common probability density function fx to be e to the power minus x greater than 0. So what I can say, that f x is equals to e to the power minus x greater than 0 for random variable x, and f y is equals to e to the power minus y greater than 0 for x random variable and for y random variable. Okay, basically they both have a common probability density function. Now u and we are considering to be u to be x plus y and v to be x upon x plus y. Okay, now first we need to check that whether x and y are independent, or sorry, whether u and v are independent or not. So in order to check that, first we need to find the marginal, or I can say the distribution of u and v. Okay, so to the density of u and v, and I will say and I will find out the joint density of u and v. Then I'll compare that whether the joint density is a product of the marginals or not. And so yeah, so we need to find out the distribution of u and v and the joint distribution of u and v. So for that, since u is equals to x plus y, v is equals to x upon x plus y, so both are continuous transformation of x and y. So we can consider that theorem which we have discussed. So we'll find out the inverse. So for that, let x plus y will be equals to u, and I will find out the value of x and y in the form of u and v, and x upon x plus y is equals to v. Now x plus y is u, which implies that x is equals to u into v, and since y is equals to u minus x, so this will imply that y is equals to u into 1 minus v. So these are basically the inverse images. So x is equals to uv and y is equals to u into 1 minus v. So for that, I will first find out the Jacobian. So what will be the Jacobian? So it will be the derivative of this with respect to u. So that is v. And derivative of uv again with respect to v, that will be u here. Now derivative of this with respect to u, that is 1 minus v. And derivative of this with respect to v, so that will be minus of u. And if I find out the determinant, it is minus uv plus u minus, sorry, not plus u, so it will be minus uv minus of u into 1, that is u minus uv. So that is minus uv minus u plus uv. So this is equals to minus u. So mod of j will be u here. So what will be the joint density of u and v here? So it will be f x comma y. Okay, so it will be here the inverse images. So inverse images are what? uv and u into 1 minus v. So so it is uv comma what was that? U into 1 minus v. So it is u into 1 minus v into the mod of the Jacobian. So it will be into u. Okay, now what is the joint density of x and y? Now since x and y are IID random variables, so the joint density will be the product of the marginals. So what we have, that the joint density f of x comma y is equals to e to the power minus of x plus y, where x comma y both are greater than 0. Okay, so this is just the product, and we have just summed up the powers in the exponential distribution, in the exponential term. Okay, now we have this joint density, so we'll just put it here. This is xy. So f u v u into v is equals to, so we'll just, in the place of x we'll write that uv. So it is uv plus this u into 1 minus v, which is u into u minus into uv. Okay, and we have u in the coefficient term. Now we have x and y to be greater than 0. So here we will have uv greater than 0 and u into 1 minus v greater than 0. So this will be the density. Now what we notice here, this will get cancelled. So f of u comma v uv is equals to u into e to the power minus u. So u into e to the power minus u. You just notice one thing here, that uv is greater than 0. Now what is u and what is v? So here u is basically x plus y, and x and y both are positive, so u will always be positive, and x and y both are positive, so v will always be positive. So u and v both are positive. Okay, now here, so first condition is true for all uv, for all uv. Now u into 1 minus v should be greater than 0. Now for this to hold, u is positive, v is positive. So 1 minus v should be positive. Okay, because this product should be positive, u is positive, so I can say that v 1 minus v should be positive, which implies that v should be less than 1. Okay, so here we are considering that u is greater than 0, but v should be less than 1. So this is basically the domain on which this density is positive. Otherwise it will be 0. It will be 0 otherwise. Okay, now so this is basically the joint density of u and v. Now I will find out the marginals of u and v, that what are the distributions of u and v. So in order to do that, what I should do, f u will be integration. So it will be the integration of the joint density with respect to v, and the limit of v will be, it is less than 1, so it will be 0 to 1. So it is greater than 0 and less than 1. Okay, so it will be integral 0 to 1 u into e to the power minus u dv. Since there is no term of v here, so it will be u into e to the power minus u. Okay, here u is greater than 0. Now, if I need to find out the marginal of fv, so fvv will be integral fuv with respect to u, and the u is running from 0 to infinity. Now it will be 0 to infinity u into e to the power minus u du, and here v is from 0 to 1. Now if I integrate this term, it will be integration of first function as such, integration of second. So it will be minus e to the power minus u minus integration derivative of first one will be this will be first, this will be second. So derivative of first will be 1 and integration of this will be e to the power minus u and negative also, so it will be like this, and it will again be minus u e to the power minus u, and this is minus e to the power minus u. So this is from 0 to infinite. So upper limit will give you always 0 and the lower limit will give you 0 here, 1 here, so it will be 1. Okay, so it is 1 for 0 v less than 1. So you can notice that v has nothing but a uniform distribution for the interval 0 to 1. Okay, so this is the marginal of u and this is marginal of v and u. Now if I find out the product of both of them, it is nothing but u e to the power minus u for u greater than 0 and v between 0 and 1, which is nothing but the joint density. So they are basically, so which implies, now since f u comma v u v is equals to f u u into f v v, this implies u and v are independent. So is that clear to you? Is there any doubt in this question?
Ma'am, could you please explain it again, ma'am?
Okay. So from the beginning only?
Yes, ma'am.
Okay. So what we have two random variables x and y, where the probability density of both the random variables is same. That is fxx is equals to e to the power minus x. So what for x I can represent it in this way and for y it will be this way. So the densities are basically same. Now if I consider two random variables u and v, which is nothing but x plus y and x divided by x plus y, then I need to check whether u and v are independent or not. Now, if I need to check this thing, then I should find out the joint density of u and v and the marginals of u and marginals of v. And I will see that whether the product of the marginals is equals to the joint density or not. Now, for that, I will use that theorem which I have stated in the in the beginning of the lecture, that we'll just find out the inverse transform in the inverse transformation. I just put it in the joint density of these two. So what I will do, I will just equate the x plus y to u in order to find the inverse images, okay? And x upon x plus y to v. Now here from here, I will find out that here from here, I can have that x is equals to v into u, because x plus y is u. Basically, I have two equations. This is equation 1 and this is equation 2. I need to solve this equation such that I can represent x and y in terms of u and v. Now, if I solve this, from the first one, I have x plus y to be equals to u. So x will be equals to u into v. Okay. Now from the first, I have y is equals to u minus x. So y is equals to u minus x and x is nothing but uv. So y is equals to u into 1 minus v. I have just taken u as common. So x is uv and y is u into 1 minus v. So I have these inverse images. Okay. So these are the inverses. Okay. Now, in order to find the joint density of UV, I should find out first the joint density of X and Y. Now, X and Y are independent random variables. So, the joint density will be the product of the marginals. So, here the joint density XY is equals to e to the power minus X into e to the power minus Y. So, it will be e to the power minus X plus Y. So, this is the joint density of this thing. Now, also for that theorem to apply, I should find out the Jacobian matrix. So that Jacobian is nothing but this is equals to for this inverse, I need to find out the derivative of this with respect to u and the partial derivative with respect to v. So partial derivative with respect to u will be v. So I've just taken it as v, and partial derivative with respect to v, I've taken it to be u. Then I need to find out the partial derivative of y with respect to u and with respect to v. Then I'll just put it here, this 1 minus me and minus u. And I'll just find out the determinant of this matrix, which came out to be minus u. And since I need to take the modulus term for this, so it is u. Now the joint density of uv will be the joint density at xy, for xy at point uv, which is the inverse image, and u into 1 minus v. Okay, so these are the inverse images. into u. So this was basically the theorem which we have stated. I'm just using that theorem. Now for this, so this is a joint density of xy. So it is nothing but e to the power minus x plus y. So in place of x, we'll just put uv. In place of y, we'll put u into 1 minus v. So it is minus of uv plus u into 1 minus v. So I've just taken it to be inside. Now this x and y should be greater than 0 for this joint density. So for our case, our uv should be greater than 0 and u into 1 minus v should be greater than 0. So the joint density will be of the form u into e to the power minus u. Now here, this for this I can say this uv is greater than 0 and u and v are always greater than 0, so it will be greater than 0 for all uv greater than 0. But u into 1 minus v, for this quantity to be greater than 0, v should be less than 1. Otherwise, this quantity will be negative. So v should be less than 1. So in order to do that, we have just taken u to be greater than 0 and v to be between 0 and 1. So this is the joint density and it will be 0 otherwise. Now we need to find out the marginals. So in order to find out the marginal, I will just integrate the joint with respect to v for marginal of u, and I will integrate with respect to u for the marginal of v. After integrating, I got this u into e to the power minus u greater than 0 for the marginal of u, and this is for the marginal of v, which is 1 for v 0 to 1. So basically, if I product these two, the marginal of u into marginal of v, so it will be u into e to the power minus u with u greater than 0, v between 0 and 1, which is nothing but the joint density. So this is same. So here I can say that u and v are independent random variable because the joint and the product of the marginals are equal. So this was about this. So is that clear now?
Yes, ma'am. Thank you, ma'am.
Okay. So I'll move forward for the next question now. So here the question says that test results from an electronic circuit board indicate that 60% of the board failures are caused by assembly defects, 25% are due to electrical components, and 15% are due to mechanical defects. So there are three scenarios. So 60% are due to assembly defect, and 25% are due to electrical component, and 15% due to mechanical defect. Okay, so suppose failures are recorded at 12 randomly selected board. So we have just selected 12 randomly board, and we are just recorded the failure. That's that. So we have now x1, x2. So 12 boards we have recorded. Now for each x1, for each xi, what we say that okay, this is failure. Now this failure is because of what? Is it because of the assembly defect, or is it because of the electrical component, or is it because of the mechanical defect? So you can say that for each xi, there are three possible outcomes, that is due to assembly defect, due to electrical component, and due to mechanical defect. So for each xi, there are three possible outcomes. So what we can say, and now here the random variable we are saying, okay. So here let the random variable x, y, z denote the number of failures due to assemblies. So what x, y, z and x, y and z are? So x, y, z. So this is a random variable which counts the number of defects due to assembly and due to assemblies, and it is the number of defects due to the due to the electronic, due to the electrical, and due to the mechanical, due to the electrical and due to the mechanical. In total we have 12, we have just selected the 12 boards. So we can model this situation with trinomial distribution. Okay. So by the use of trinomial distribution, we can model this situation, because for each xi we have three outcomes. I can have assembly defect, electrical defect, or mechanical defect. And now, so here x will count that how many assembly defects are there, y will count how many electrical defects are there, and z will count how many mechanical defects are there. So we can just model it using the trinomial distribution. So we need to find that probability x is equals to 7, y is equals to 3, and z is equals to 2. Okay, so what was the density for the trinomial distribution we had? So here, this is also the size is 12. So we have total 12 boards selected. So it will be equals to 12 factorial divided by 7 factorial, because here we are taking x to be 7, 3 factorial, this to be 2 factorial. Okay, then what is the probability for the this outcome due to assembly? What is the probability due to assembly? So the probability is 60 by 100. So the probability is 60 by 100. So this is nothing but 3 by 5. For the electrical component defect, the probability is 25 by 100, which is 1 by 4. Okay, and for the third one, we have the probability to be 15 by 100, which is 3 by 20. 3 by 5, 1 by 4, and 3 by 20 are the probabilities for such outcomes. So here the probability for the first one, which was 3 by 5. So 3 by 5 to the power 7, and the second one was 1 by 4. So 1 by 4 to the power 3, and 3 by 20 to the power 2. Okay. So this is just the trinomial distribution. You guys just calculate it. Just let me know that what the answer is coming. So 7 factorial, if I cancel it, so it will be 8, 9, 10, 11, 12 in the numerator. And here I have 3 factorial means 6 into 2. And here 3 by 5 to the power 7, and 1 by 4 to the power 3, 3 by 20 to the power 2. This is 2 4 times, 3 times, and 3 3 times. So it will be 60 into 11, 11 into 12 into 3 by 5 to the power 7, 1 by 4, 3 by 20, 1 by 5, 4 by to the power 3, and this to the power 2. So what will be the answer for this? Just calculate it.
Zero point 0779.
Okay. So the answer is 0.0779. Okay. So any doubt in this question? Okay, then I will move forward for the next one. So here the question is that the Cartesian coordinates x, y, z of a random point moving in space are mutually independent. So these are Cartesian coordinate x, y, z. Okay, now each of which is normal. So x, comma y, comma z, all are standard normal random variables. Now let the random variable w denote the distance of a point from origin. So anyone can tell me that what is the distance of a point from origin? If I need to find the distance of the point x, y, z from the origin, then what will be the w? W is the distance. What will be? So what will be the distance from the origin?
X square plus y square plus z square square root of all three, sum of.
Yeah, so it will be under root of x square plus y square plus z square.
And here the x, y, z represent the coordinate.
Yeah. So this is basically the coordinates. So W will be the, so basically x, y, z are the random variables. So they will be varying. So the distance also will be varying. So basically we are just taking the values of the distance. So W is a random variable which is noting the distance, and x and y and z are the normal random variables. So they can have different values which are basically the Cartesian coordinates. Now W will be this thing. Now what we need to find that the distribution of W and W square. So W square will be, x square plus y square plus z square. Now note one thing here, x follows normal. So this implies that x square will follow chi square with 1 degrees of freedom. Y square will again follow chi square with 1 degrees of freedom. Z square will again follow chi square with 1 degrees of freedom. So which implies that W square follows chi square with 3 degrees of freedom. Is it okay?
Yes, ma'am.
So W square follows chi square with 3 degrees of freedom. Now, if I want to find out the density of W, okay, or the distribution, I can say, or the density of W, then for that, what I need to do, that if I consider, so W square is chi square, so let's first let U is equals to W square, okay, which follows chi square with 3 degrees of freedom. So let first write down the density of U. Why I'm writing so? Because I need to find out the distribution of W. Okay, so W will be nothing but under root of U. So if I find out the density of U, then from that density I can find out the density of W. Okay, so first of all I'll go towards the density of U, that is W square. Since I know that the density of it is chi-square distribution, so I know the density of chi-square distribution. So FUU will be what? So in general it is, so just write this. So it is, in general it is e to the power minus u by 2, u to the power n by 2 minus 1 divided by 2 to the power n by 2 into gamma n by 2. So this is basically the density for the chi-square distribution. Okay. And obviously because it is a chi-square distribution which is square of standard normal, so u is greater than 0. So this is the density. Now here n is the degrees of freedom. So in place of degrees of freedom, we have 3 degrees of freedom. So we'll just replace the n by 3. So what it will be, FUU is equals to e to the power minus 2 by u by 2, u to the power 3 by 2 minus 1, which is 1 by 2. Okay, divided by 2 to the power 3 by 2, gamma 3 by 2. So it will be e to the power minus u by 2 under root of u divided by 2 to the power 3 by 2. Now gamma 3 by 2 is nothing but 1 by 2 gamma 1 by 2. So 2 will get cancelled, one of the 2 will get cancelled. Gamma 1 by 2 is under root of pi. So it is e to the power minus u by 2. So it will be under root of pi, and this 3 by 2 minus 1 will be 1 by 2, so it will be under root 2 pi. Okay, so and there we have under root of u. So we have FUU is equals to under root u, or I can say u to the power 1 by 2 e to the power minus u by 2 by root pi 2 pi, u greater than 0. Okay, now we have the density for u. Now what we know, that W square is equals to u, which implies that W is equals to under root of u. Okay. Now notice here one thing, that W is equals to under root of U. Now since we are taking the under root, W is equals to under root of U. So W can be plus minus under root of U. We can have two scenarios that W can be plus minus under root of U. But since W is distance, basically. Okay, so W is a distance, so it cannot be negative. So which implies that W is equals to under root of U. Here also I will correct it. I am not written it. Okay. So W will be under root of U. Now since W is a under root of U and I'm considering only the positive under root of U. So what will be the density of W? So F W will be, we'll find out the inverse. So inverse will be under root of U is equals to W. So U will be W square. So this is basically the inverse. So F U of W square, because this is the inverse. Okay, and I will differentiate it. So the derivative of this will be 2 into W. Okay, now for this, W should be greater than 0. Now this is nothing but, in place of U, I just need to write W square here. So it will be under root of U, in place of U I need to write W square. So it will be W e to the power minus W square by 2 divided by under root of 2 pi for W greater than 0. So this will be the density of W.
I'm into 2W.
Yeah, sorry, into 2W.
No,
Yeah,
so,
2 is there.
so it will be W square.
No, here 2W, so it will be W square. Yeah. Because one of the W square we are putting it here, so W will come from here, and 2W also we have, so it will be 2W square e to the power minus W square by 2 divided by under root 2 pi. So this will be the density of W. Okay, now if it was not a distance, then for both of the scenarios, for plus W plus U and minus U, we need to find out the density. Okay. Now for the next question, so what is the next question? That x1, x2, x3, x4, x5 up to x7 are independent and identically distributed random variables with common PDF this. So this is basically a uniform random variable over the interval 0, 1. So suppose that x3, so basically x3 is the, I can say the third smallest. Okay, third smallest random variable. So the density, or suppose the that x3 is of the density of the x3 PDF of the x3 is of this form: a y to the power b 1 minus y to the power c 0 y is between 0 and 1. Then what is the values of a, b, and c? So first of all, for this I need to find out the density or the marginal density of this random variable x3. Okay, so we have all this x1, x2, x7 random variables, and I need to find out the random variable which is at third point if I'm ordering it. Okay, so the density, as I've discussed, is given as f, let y3 is equals to this. Okay, so f y3 of y is equals to, so what was the formula for that? So it was given as, so it was n factorial, so 7 factorial divided by r minus so it was, I'm finding out the density. Okay, r minus 1 factorial, which is 3 minus 1 factorial, into I have n minus r factorial, which is 7 minus 3 factorial. Okay, into the distribution at y3 to the power r minus 1, that is 3 minus 1, into 1 minus the distribution at the point, not y3 here actually, because I am taking the argument to be y, so I will take it as y. Here I am taking it to be y, that's why I am taking here to be y. Okay, so fy, 1 minus fy to the power n minus r, so it is 7 minus 3, into the density f at y. Okay, so here since you know that the density is given as to be 1 for x 0 to 1, so this quantity, this will be 1. Okay, now what will be the distribution? So from there, if it is a uniform density, so distribution fx is equals to integral 0 to 1 0 to x into fx dx, so which is nothing but x only, okay, for x 0 to 1. So the distribution is giving it to be x. So here we'll put it here. So it will be y here. So f of y3y is equals to 7 factorial divided by 2 factorial into 4 factorial. So 7 factorial divided by 2 factorial into 4 factorial into f of y. So it will be y to the power 2. So it will be y square into, this is 1 minus y to the power 4. So it will be 1 minus y to the power 4, and here it will be 1, where y is ranging from 0 to 1. So it will be nothing but here this is 4 factorial. So if I cut it, it is 5, 6, 7 there upon 2, y square into 1 minus y to the power 4, and it will get cancelled, and it will be 21 into 5 y square into 1 minus y to the power 4. So it will be 105 y square into 1 minus y to the power 4. So here we have this format. So here a will be 105. So a is 105, b is 2, and c is 4. P is here the power of y, and c is the power of 1 minus y. So it is 2 and it is 4. So is that okay? So this is directly from the expression for the marginal density. Okay. So is it okay? Is there any doubt in this question?
No, ma'am.
So this is fine. Okay. Then I will discuss one more question. So this is a question uh, on bivariate normal distribution. Okay, so x and y are two continuous random variable with joint PDF as given by this quantity. Now this you can see that this is a normal bivariate normal distribution format of the density. So here we have this minus 1 upon 0.72 x minus mu upon sigma whole square plus y minus mu upon sigma whole mu y upon sigma y whole square minus this quantity and all these things. So from here we can conclude that this mean for the random variable. So if I consider, so x will be a normal random variable again with mu x and sigma x square, and y, I know that x and y are bivariate, so this will be sigma y square. And here from this expression I can say that mu x is 2. So this is normal 2 comma sigma. What is sigma? Sigma is 2 here. So it will be sigma square will be 4. So it will be normal 2 comma 4. And for the y random variable, it is 1. The mean is 1 and the variance is, because standard deviation is 1, so variance is also 1. So it is normal 1 comma 1. So we can say that expected value of x is 2 and expected value of y is 1. Now what about the covariance of x comma y? What is the covariance? Covariance is rho into sigma x into sigma y. So which is nothing but sigma x is 2 and sigma y is 1. So it is 2 into rho. What is rho here? So we know that in this density, what is the format basically? So we have fxy x comma y is equals to 1 upon. So what is the format of the density for the bivariate normal distribution? So wait a minute. We have 1 upon pi into sigma x into sigma y into rho under root of 1 minus rho square, then exponential of this term in here. So here we have the coefficient to be equals to this quantity. So this implies, which implies that pi into sigma x into sigma y under root 1 minus rho square is nothing but this 2.4 into pi. So 2.4 into pi. Sigma x, sigma y, this is pi will get cancelled. And what is sigma x here? Sigma x is 2 and sigma y is 1. So it will be 2 here. So it will be 2 under root of 1 minus rho square is equals to 2.4. So 1 minus rho square is equals to, it is, so 1 minus rho square is equals to 1.2 whole square. So it will be, so yeah. So so we have this to be equals to sigma x and sigma y to be equal to 2. So it will be 1 minus rho square is equals to, so here we have what? 2.4 into pi. There's some mistake. So you guys have seen the expression for the bivariate normal distribution. Is there any mistake in this? Is there any mistake in this expression?
Isn't it 2 pi?
What? Just check it once.
But this was the question in the exam as well.
Okay, in the exam it was a question.
Yes.
So you must have done the solution for that also.
Yeah, but I will have to find the seat.
So okay, so the thing is that so the density, the format of the density is nothing. So here we have 2 here actually.
Yes. Yes, because generally it's root of root 2
Yeah,
pi.
root of 2 pi into root of 2 pi. That's why it
Yeah.
is 2 pi. So here 2 is there. So that I missed. So it will be 2 here. So it will be, okay. So it will be 4 here. Okay. So 4 here. So it will go there. So it will be 0.6. So it will be 0.6. So this is 0.36. So 1 minus 0.36 is the rho square. So which is
64.
0.64 will be the rho square. So which implies rho is 0.8. And it is positive because it is a, so rho is, we are taking it to be,
It is positive because the in the expression or exponent it is minus 1.6. If it would have been positive,
yeah,
then it would have been negative.
yeah. Because it is minus 1.6, so that's why we will take it as a positive quantity. Okay, so yeah, this is all about this question. So you have done this question in the exam?
Yes, ma'am.
Okay.
Easiest of the whole questions in the exam.
Yeah. So how was the exam now? The questions were like,
Not exam, it was basically the not the
okay, the
exam
assignment they
assignments.
have posted. Yeah.
Yeah, sorry, the I'm saying exam is still a bit later.
Okay. So you guys are able to solve all the questions which are given in the assignment, or how is it like?
Yes, yes, ma'am.
Okay. So you people have registered for the course or just enrolled it?
No, ma'am, I have registered for the course.
So anyone of you have registered for this course?
Yes, ma'am.
Okay, you have registered. So when is the exam for this?
I think uh, in April. I think 27th of April something.
Last of it.
Um,
Yep.
May 3rd, ma'am.
Oh,
Okay,
sorry.
May 3rd.
Yes, sir.
Yeah, so till that time we'll be able to finish all the lectures and the tutorials. So yeah, I think these questions and all these things are helpful to you. So if there are something or any doubt, then you can just ask.
Yes, ma'am. No, oh, no, ma'am. Sorry. Thank you. No.
Okay, so if there is any doubt, then you can ask, or I will be ending this meeting for today.
No, ma'am. Thank you.
Okay, thank you. Okay, okay, then I will be ending this meeting. Thank you, guys.